Hello everyone. My name is Quintus. I'm from the Flashbots research team, and today I'll be talking about secure hardware. The sort of premise and the context for this talk is that, as the quote goes, software has eaten the world, and as most of you may know, software doesn't run literally in the cloud. It always runs on some actual hardware. And so all of the digital technology that we rely on today actually means that we rely on hardware. And so this applies to the cars that keep us on the roads, the planes that keep us in the skies, our hardware wallets in our, somewhere safe, I guess, your password manager on your phone, the server your bank runs on, all of that. Every time we use these technologies, we make the assumption that the hardware that is supporting this technology is actually working in the way we expect it to work, and is not actively working against us. But this foundation is not nearly as secure, or rather we have no reason to believe that it is secure, and that's kind of the topic of the talk today. So this is from Ledger's website. For those of you who may not know, Ledger is a very popular hardware wallet. Now, Ledger has every incentive to convince their customers that they are super secure and that the hardware is, serving you and protecting your keys. But if you look at their website, what is actually the case is that even their low-level software, some of it, has to be closed along with the full hardware design. So this means that you are trusting the hardware providers, you're trusting Ledger, that the hardware is not, it doesn't come with a backdoor, that it actually has the defenses that you expect it to have. And this isn't a Ledger-specific issue. Because of the difference between the open hardware, open source design, open fabrication process, because of the difference between that cluster of things and the closed alternative, hardware companies have this choice between more secure, more performant, more cost-efficient products and improving their trust assumptions. And the difference is so stark that pretty much everyone has to, in some way, choose the more efficient outcome and take on board these trust assumptions. Now, the reasoning behind this is quite sound in some regard. The user mistakes, software bugs, all the thousands of hackers out there who don't have access to your device, these are more legitimate threats. And if we were trying to secure a system tomorrow, these are the attacks we'd spend most of our time on. The more difficult attacks that can be executed by fewer actors are much less likely, and these are the attacks that require access to the hardware or to be implanted in the manufacturing process. But I don't think that this is actually a good reason to dismiss worrying about hardware security. And one reason for that is that there actually just have been a lot more vulnerabilities than people have realized, or that I was aware of before I looked into this. And you have to ask yourself if there are examples of governments implanting backdoors into hardware, of corporations potentially under the influence of governments implanting these kinds of backdoors. What reason do we have to believe in this world where all of the hardware is closed anyway, that there aren't like active hardware backdoors, active Trojans among us right now, like in this room? And then another angle to this is just that you may not expect a hardware manufacturer or someone in the hardware supply chain to be malicious, but they could just be lazy. They could be selling you chips that are not up to scratch. And so you expect to get a certain level of protection when you buy this hardware, and in reality it is just a much lower degree of protection, and you have no way of validating this, or it's much harder to validate. And this is an example from one particular study a couple of years ago. So one part of my motivation here is like this old piece of wisdom that if you're going to build something, you want to make sure that the assumptions that this system relies on are strong. Because when the going gets tough and your foundation is not strong, things collapse pretty remarkably. And I guess the image I always have in my mind is you think of all these cars on the roads, or everyone who's using a ledger, so much value in the crypto ecosystem that's could be attacked in one fell swoop, I guess. But another more optimistic take on this sort of securing this rant, I would say this talk is in favor of securing hardware, is that there is a growing movement, I guess, in the crypto ecosystem and outside of it, like the OpenAI quote I have up there, to use assumptions in secure hardware to actually do more than we have been able to today. We are in an industry of improving trust assumptions, and secure hardware provides us with another primitive to improve these trust assumptions and unlock new use cases. And so if we are able to improve these trust assumptions in the hardware, we will actually be able to do more with that to facilitate trust in more performant use cases that cannot be served by traditional cryptography, or to bolster the security that to bolster the security assumptions that go behind the software cryptography schemes we use, like honest majority assumptions in MPC protocols. So I'm not here today to just say that this is something that we should pay attention to. I am here to say that this is something we should pay attention to, and that it is something that we actually can do something about. There is no technical reason, or no obvious technical reason that we cannot address this problem. And to make that case, I'll briefly go through some of the research that's out there today that, taken to its completion, constitute some of the puzzle pieces that we can put together to solve this problem. So we can break out this problem for most hardware into two sub-problems, and then I'll speak about two other ones. But the first is taking a piece of hardware and being able to actually look at it and see what is going on, imaging this piece of hardware. And the other is having something to compare that image to. There's no point in being able to look at a piece of hardware and see all of these wires and transistors and not being able to compare that to something for which we understand the logic. So first, understanding the imaging, I'll point to one sort of research direction pursued by a legend called Bunny. And for context, what has been the issue in the hardware imaging world for a while, or like one of the issues, is that imaging techniques are destructive or very, very expensive. What Bunny has pioneered is using shortwave infrared light to image chips without having to destroy them, without having them to ship them to having them shipped to a facility in Switzerland the size of several homes. And this is actually something that we ideally could scale so that there's testing facilities and multiple in a city, and maybe some running at home if you're very serious about it. As for a reference, this is a really challenging problem, and probably the one that we as an ecosystem can put much of our weight behind. Currently, as I was alluding to earlier, so much of the technology that we rely on is closed. And there are projects that are taking this problem on head-on and are directly working on either developing their own open source IP or on, I guess, purchasing from other people. And they are moving this barrier of trust lower and lower and lower, but still they have not been able to open source the information we'd need to be able to assert that this piece of hardware does not contain a hardware backdoor. And their motivations are pretty pure from the other open source angles. They want people to be able to iterate on their designs and to not be worried about vendor lock-in, but the security angle is still not completely addressed. And so one thing we can do is we can add our weight to this movement and push for completely open source designs. But there are also many pragmatic ways to get around this problem, in which we navigate, without going into the details, we navigate this problem of having fabs which don't allow for the low-level design descriptions of chips to be made public, to circumvent these closures using ZK proofs of chip validity and other forms of proofs. And I'll link to something at the end that goes into that. And so solving these two problems solves the easy case. And so this solves a case for hardware that you have physical custody of. This is for your phone, for your ledger. And solving this has already changed the world, I would say. But I was talking about TEEs earlier and using secure hardware to be able to assure someone who doesn't have physical access to the device that the hardware is operating correctly. To address this problem, we need to solve two other sub-problems. One is how we generate a key and tie it to the hardware in such a way that we can be convinced that the key is not compromised and is uniquely available to the logic in the hardware. The sort of magic answer here is puffs, which are really interesting technology that use the inevitable randomness in the manifestation of the chip, in the physical chip, to create a secret. And so anyone trying to investigate the chip to get to the secret inevitably disturbs the chip structure, destroying the key. Pretty cool technology. And one that has actually been tested out, and there are existing puffs in the world today. It's not like spacey magic. Then on the attestation front, the question is, how do we now allow someone to investigate a physical chip and then convince a remote user who doesn't have access to the physical chip that this chip is what they expect it to be? And in order to do this, there are actually some investigation protocols, some verification protocols that we can implement where the user has to only assume that some threshold of actors in a committee is honest or rational. And there's, we've proposed one specific protocol for doing this, but there are many improvements that can be made to it, and so I'll encourage you to have a look at that. The real point that I wanted to make today is that, look, this is a very important problem, and it is a problem that we can solve. We've mapped out some of the technologies that can solve these problems. We've mapped out these sub-problems that need to be addressed to enable these technologies. What's really left, and obviously there's a lot of work left, is energy to do it, buy-in from the community. And if the large hardware companies that make trillions of dollars in their incumbent position, with the world relying on them, trusting on them, have no incentive to move from where they are in their comfortable position. If there are a group of people who can move the needle and breathe energy into this, it should be the group of people who are working on trustless technologies and the group of people who are trying to improve the trust assumptions of the world and have the ideological orientation of the people in this conference venue. So this should be something that we care about because it is an important thing that we actually can make a difference in. And so I guess my first call to action is to go look at this post that several of my co-authors and I put out, where we go into more detail about what I was describing now. There are several academic research teams that are moving the frontier. They need funding. There are several problems that people with formal methods skill sets, with hardware design skill sets in this room can address. And I think even more broadly, just having this be acknowledged as an important problem